Okay. So today we'll be covering about probability, and there's going to be a lot of formulas coming through for today's session. So probability is defined as chance or likelihood of an event usually happening, and the value that they ask for is usually between 0 to 1. So 1 being impossible for like the chance of something to happen, while 1 being certain for it to happen. So for example, if you usually it's the range of values of probability is between 0 to 1 because its form of it is usually in percentage or fraction. Because basically, as we're going to be covering later, probability is usually in the form of a chance of a happening over all the probability that the probability that any outcome will come true. So we're going to have to know a bit of some of these terms when it comes to probability. So in experimental probability, or usually probability in relation to experiments, like scientific experiments, there are several terms that you need to be familiar with at least. So the first would be number of trials. Number of trials is the number of experiments or the number of repeated experiments. For example, if you have an experiment where you have someone who's blindfolded and you ask the person to take marbles from it, from bag A, and then you ask them to take another marble from bag B. So technically, if we have this kind of setup of an experiment, that would be one trial. Then if you ask the person to repeat the process, take one marble from bag A and then take one marble from bag B, that's what you call 2 trials. So the number of trials in this case would be 2. Basically, it's just the number of how many times you repeat the experiment. And then there's also the term outcome. Outcome is essentially like the number of possible results from the experiment. And usually this is not yet in form of 0 to 1. In this case, you're mostly usually noting like the chances, the list of the possible chances in terms of numbers. And that's what you call, that's like specifically when it comes to the numbers of the outcome that is observed, that's when you refer to it as frequency. So for example, you roll a dice. You have someone roll a dice for you, like the 6-sided die, and then the person rolled some of these numbers. So after rolling it several times, they get this data. And if they ask you what is the frequency of number 2, then that would be 3 times. And in this case, the number of trials that you have would be 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 number of trials. And since for the outcomes, there's 6 sides in a die, right? And there's 6 numbers. To find all the possible outcomes of this sided die, there's always a chance for you to get any of these numbers equally. So the possible outcomes when you roll one die would be 6 outcomes. And so if you want to find the relative frequency of rolling a die, let's just say we want to find the relative frequency of rolling number 1. So since between numbers 1 until 6, there's only one number 1, and you divide it by the total outcomes of it, which is 6 outcomes, then the relative frequency of rolling the die as 1 will be 1/6. And that's, it gives a brief introduction to some of the general terms that you're going to come through when it comes to experimental probability. There are a lot of ways to portray this probability or to show it. And some of the ways that you're going to learn is the two-way tables, the 2D grid version, the 2D grids, and tree diagram. And usually, I think the more common ones that we're going to be using is going to be the two-way tables or the tree diagram. So the two-way tables is a way to usually compare two distinct categories with several variables inside. For example, in this case, we have the category of students taking diplomas and their gender. So the reason why we usually do this in terms of probability is because it's going to be easy for you to look for the relative frequencies that you want to find or the probabilities that you want to look for. So for example, if you want to look for the relative frequency or the probability of encountering a student who is a male IB, then that would be 25, see right here, 25 over, let's just say we're trying to look for the chances for you to, the relative frequency for you to find a male IB student between all the students in this particular school or in this particular data. So that would be 25 over all the total outcomes, which would be 25 plus 12 plus 45 plus 39 plus 9 plus 53. All of that. So it's very effective to help you find probability, especially if the data is, I think, independent. Well, this will be explained further later because there's going to be a lot of explanations for that. And then next up, we have probability, especially in terms of Venn diagrams. So as we learned before in chapter 2, we learned about how the universal set, or the U, is this particular rectangular shape. In probabilities case, this is what you call as the sample space. And the sample space is essentially the space where all the samples or all the outcomes are in. And the circles in the Venn diagrams would be usually what you call as events. So the events are always a subset of the sample space because the events is always inside the sample space. It's not possible for the events to be bigger than the sample space since since that's not, if the event is outside of the sample space, then the event is probably like a separate situation from this one. And then you also have the outcomes as events. Sorry, the outcomes as elements. So as you can see right here, if we have A in this particular circle, let's just call the circle X. Let's just call this circle or this event X. So the people who only do X would have an outcome of A. Okay, let me just rewrite this in a more appropriate way. The outcome of X only would equal to A. So this outcome is an element. And then there's also alternatives to illustrate sample space and events, such as the 2D grid, two-dimensional grid. For example, we have something like this. And let's just say we want to portray a grid where you flip a coin twice. So the chances of flipping a coin would be tails and heads, right? And if you flip a coin twice, then all the possible chances of getting heads or tails would be as follows. Tails, and then tails, tails, heads, heads, tails, and then heads, heads. So if we draw it like this, it would be something like this. So this is HD, this is tail tail, this is head heads, this is TH. And last but not least, we have the tree diagram. The tree diagram is usually the ones that branches out. For example, let's just say we have there's a chance tomorrow. Tomorrow you have like 1/3 chance of rain. So if the other event other than rain would be to be sunny, to not rain. And since the chances of raining is 1/3, then the chances of not raining would be the complementary event of it, or the opposite probability of it, aka 2/3. So let's just say that every day you have a chance of you have a 1/3 chance of raining. So in the next day, you have 1/3 chance of raining and 2/3 chance of being sunny. And then it will be the same in the case of being sunny. So this is how the tree diagram works. I think like between all these what do you call, all these ways to illustrate probability, it really depends on how the question works or what the question is. Usually typically if you have questions that are reliant on dependent events, I would personally tend to prefer to use this. But then um, if you have questions with Venn diagram notations, I personally would usually use this. But I think like any sort of strategy would work as long as you're comfy with what you're doing. Because most of the time, the Venn diagrams can be um, replaced by the tree diagram versions. So, like in the end, it's really up to you on how you want to illustrate it. Okay, so like I said before, in theory, probability is denoted by the number of A outcomes over all outcomes in sample space. So if you want to write it in terms of notation, that would be N A over NU. Remember that the notation N refers to the number of elements in their sets. And so most of the time, when it comes to theoretical probability, since, for example, a set like this is usually one event, the opposite of the other event is usually the other option, the other only option other than the first event. So if you add up those two, you're going to get one. Since you're combining the chances of two different events that are the complete opposite of each other. So like it's like you can't get the other how do you say it? It's like the same as doing this. Especially because PU equals to 1. Okay, so next up, we have this thing where sometimes you have probability and you want to find the number of times when something occurs. For example, in terms of rolling a dice. Like we said before, if there's 1/6 chances of rolling 1 in the dice, then if you roll a dice, let's just say 36 times, how much ones would you get? That's when you would use the 1/6 chance times 36. So that would give you the approximate number of times when getting one occurs. Because in real life, you won't necessarily exactly get 6 if you roll dice 36 times, because despite it being equally possible, it's still random chance. So there are chances when you roll a dice 36 times, you might get like 5 ones, or perhaps you might get 7 ones, or even if the random chance is like very, even there are also times when you might only get 3 ones, which is incredibly rare, but possible because of the random nature of rolling a dice. But with this, we can get the average approximation of the number of times you get the event. Okay, so further into this, we're going to go into more into Venn diagrams, more like Venn notations actually, and probability. So remember that in chapter 2, we learned that, for example, if we have set A and set B in a universal set, we have A and B, which is this part, and we also have A union B. So this is A intersection B. This is A union B. And A union B is basically, well, either A or B. So often, if you calculate this thing mathematically, then you can get P A union B plus P A union B equals to P A plus P B minus P A intersection B. So the reason why you have this formula is because it's like basically trying to get this is essentially you can get it by doing A plus B, and then since the value of this is double, you minus it by itself. So you get the value of this, which in return is the result of this. And that's, who added hearts there? That's basically how you get that. And then there's also another situation where set A and set B can be mutually exclusive. And mutually exclusive means that it has no intersection because it's like a separate situation. And when that happens, P A union B equals to P A plus P B. This again is actually quite similar to the Venn diagram formulas that we encountered last time. Okay, so now we have independent events. So independent events is what happens when one event doesn't affect the event of another. So an example of an independent event would be something like um, there are several examples for this. For example, we have tossing a coin. If we toss a coin 2 times, then the result of the first one will not affect the result of the second one. Or another example would be throwing a dice. If you throw a dice, the first result, if we want to look for the probability of getting 1 in the dice, then the first time you throw it, the chances would be 1/6. And then the second time you want to throw it, the chances will again be 1/6. So the first event won't affect the second event. Examples of something that is not independent events, which would be called as dependent events, would be something like if you have a bag and then you try to take 1 marble outside. If you have a bag with marbles, for example, with red colors and white colors, and you take one of the marbles outside, and then you take another marble, then the first event would affect the result of the second event. Because, for example, if we have 4 pieces of marbles in the first place, then you take one, then in the bag, there will only be 3 marbles. And that means that the next time you take another marble, the chances are affected by the result of the first time you take a marble. Because in this case, there's red marbles and there's white marbles. In the first chance, you might, for example, you might take a white marble, then there's more chances for you to take a red marble. But then if you take a red marble in the first place, then in the second chance, there might be a higher chance for you to take the white marble. Presuming that this is the situation in the bag. And so for independent events, if you want to find the chances of getting the same result, PA intersection B, then you can look for it by doing PA times PB. And this would work even if you have, for example, you throw a dice 3 times. So this is A, this is B, this is C. Then that would be PA union PA intersection B intersection C equals to PA times PB times PC. But then it's a bit different for dependent events because the first event would affect the next event. Like, for example, if you have the situation with the bags and the marbles. So let's just say that in the first chance, if you take a white marble, the chances of taking a white marble would be 2/4. But then during the second chance, the chances of taking another white marble, let's just say, would be 1/3. And then how about taking red marbles in the second chance? then that would be 2/3 since the red marbles are left untouched. And so on and so on. This is going to 2/3. So so yeah, the first result affects the next result. And that's what you call as dependent events. And then there's also what you call as conditional probability. So conditional probability is when they try to look for the chances of A happening when B happens. How you write it is something like this. And basically what it asks you is the chances of there is A when B is occurring. And this is denoted by P A intersection B over PB. Since you're looking, if you insert it, it's basically, if you look at the bigger picture, it's kind of like saying P A over PU not exactly PA, more like PA union B over PU over PB over PU. So if you cross it out, it gets you this. And then for J and K, this is more of AI content. For AA, you don't necessarily have to know this. All you need to know is the conditional probability I just taught you. But for the next part, it's more of going in depth about the conditional probability itself. So, and also more in depth about independent events. So essentially what's going on is that since independent events is denoted by this, there are also other properties that comes with independent events. When you have when they're looking for the chances of A when B happens, or the chances of A when B complementary happens, then the result would be equal to the chances of A happening. Because again, the chances of B doesn't influence the chances of A. So whatever, even if they're asking you the chances of A when B is happening, then the chances of A will remain the same, no matter what. And it also applies the same for its counterparts if all the variables are independent. So the chances of B would also be the same if they were asking the chances of B in A or the chances of B when the complementary of A is happening. So last but not least, we have the Bayes theorem. Basically, this is an alternative of a formula this is actually more of like shortcut of the conditional probability formula. And basically, what happens is that, you see, if P A union B, no, if the chances of A over chances of B equals to P A intersection B over P B, then the chances of B in A equals to P A intersection B over A. They would have this. They would pretty much have the same thing, right? And what you want to do is make it so that it's more convenient for you to count it, because there are situations when in some questions they give you the probability of B in A, and then they ask you to find the probability of A in B. And to make it more easier, you make it so that you can substitute the formula and turn it so you can immediately insert the values of what you have. And this is what you call as the Bayes theorem. And the last alternative is essentially also the same thing as the Bayes theorem, but a more complicated insert of it. As you can see, they replace the probability of B with probability of B over A times probability of A plus probability of B in complement of A times probability of A. So that is pretty much it for today's theory. We should probably do a lot of practice for these, because the thing with these probability formulas is that it's hard. It's kind of a bit hard to wrap it around your head, unless if you've done some practice and try to apply it.